Hello, everyone, and welcome to this new Interalage broadcast. We are a group of Latin American Association of Space Geophysics students. Today we have Dr. Julio Mejía Ambris, who will talk about solar wind and Mexican Array Radio Telescope. He is a physics mathematician and completed his PhD in space physics at UNAM. He is currently a researcher at the UNAM Geophysics Institute and a member of National Space Weather Laboratory of Mexico. His lines of research are interplanetary scintillation, solar radio astronomy, and space weather. Well, if you have any question, please write us on our YouTube channel. Thank you, Dr. Mejía, for accepting this invitation. And you can start.
Hi, everybody. Well, as Griselda says, I'm involved with the Mexican Array Radio Telescope, and I want to talk about what we do with this radio telescope. We do mostly research about solar wind, but there are other opportunities that we can explore to study other fields. So what you are seeing is a view of the antenna. The antenna has 4,096 dipoles of 2 meters each one. They are arranged in 64 lines. So we can track the sky with 62 beams currently. Well, Mexar is located in Mexico. You can see here, you can see my mouse. It's near to Mexico City, about 300 kilometers from Mexico City. And here you can see, well, part of the South America. And we are about 19 degrees in altitude and 1,000 to the west in longitude. MEXAR is the only instrument of its kind in the Americas. In the past, there were one in San Diego, California. Now it's not currently using. And it's the only telescope in America that uses the observations to observe interplanetary scintillations, and this way we can detect solar wind. I want to talk a little more later of this. We are part of worldwide IPS stations that we join to track solar wind at different longitudes. This way we can cover all the time solar wind and detect in a better way all solar transits in the solar wind. Some of the other instruments are the Institute for Space Environment Research in Japan. Other is LOFAR, also the UT Radio Telescope in India, the Big Scanning Array in Russia, and the Murchison Wide Field Array in Australia. Well, this is again an aerial view of the antenna. The antenna displays, or the array displays beams. It's a transit station, so these beams are fixed in the local meridian. So with the rotation of here, we can track all the sky by using all the beams. Before 1920, we had a different backend, an analogical backend, and we used to use a bandwidth of 2 megahertz and only 16 beams. Now we have up to 62 beams. Also, we can increase the number of beams. And we have a better resolution to sky to figure all the sky. So the way we use the beams, here this is an image of a beam. They have 1 degree in east to west directions, so we can track the flux of the source during about 4 minutes. the flux of compact radio source during about 4 minutes. But most interested in the scintillation here, that is the flux fluctuations of the radio sources due to when the signal crosses by the solar wind and passes across solar wind irregularities. Well, this is the former analogical system. This is about 1 meter square size of the beamformer that we had in the past. Now we replaced it by 2 tiles of FPGA systems. They now can channelize bandwidth of 12.5 megahertz. Now we have 512 channels, so we can select the channels to only view with one section on all the spectrometers. Now Mexar is working like an spectrometer too. And we also, in the past, we used to have just the maximum sample per time was 20 milliseconds. Now we can sample even more with better resolution to 1 millisecond, shortest period. And in the past also, we had not so good sensitivity. It's about 12 Janskis per beam. Now we have 2 Janskis per beam. We have improved very well the sensitivity, as you can see. This is just to show all the sky, all the galaxy viewed by Mexar using the 62 beams. We can track the sky from about minus 50 degrees in declinations up to about 90 degrees in declination. So we are able to cover all the sky. And also there is a beam that is a synthetic beam, but that we can give a specific direction and a specific declination in the sky. Here you can see the map in sidereal time versus declination. You can see here structures like the center of the galaxy, Cassiopeia, while other structures that are strong in radio at metric waves. Now, we are mostly interested, as I said in the beginning, is to observe interplanetary scintillation. In the same way that you observe the stars, the scintillation, the twinkling of stars when the light crosses by the atmosphere, by the turbulent atmosphere, you can see the stars moving or like twinkling. In the same way, the compact sources, for example, nuclear active regions, when the signal in radio waves crosses by the solar wind, we also observe the twinkling of these sources as is reflected as fluctuations of the source. Now, by analyzing the statistical of these fluctuations, we can recover what is happening along all the line of sight. If we have several line of sights, we can recreate, even if there is a CME, for example, crossing by the solar wind, the velocity, density, directions. With the number of more and more radio sources looking by IPS, we can even have a better resolution to track the solar transits. Okay, this is a basic geometry of the IPS configuration. Here we have the sun, here the line of sight to the source, and this is the region where mostly we associate properties that result from the IPS. What we observe really is a radiation pattern that is projected here at here. This radiation pattern moves with the solar wind, so we can detect these fluctuations. There are two ways less to detect velocities. With two stations, I don't want to explain this, but and another using just one, like with Mexar, one single station. And the key is using the power spectra of the observations, the power spectra of the time series of the scintillation. Here's the elongation angle epsilon. This theta is represented, well, the line of sight. I'm gonna show a model using this system. Okay, the model that we use is statistics along the line of sight represented by three functions. One function represents the scintillations, Q is the wave number of irregularities, theta, the line of sight, lambda is the wavelength of observation. Another function that also represents the physics along the line of sight is the Gaussian visibility, where Q is again the wave number, theta is the size of the source. That is important because with the increase of the size, the scintillation is starts to decrease. Another parameters are turbulence of the solar winds that goes as Q, the number of wave number of the solar wind irregularities at minus alpha. Alpha is about 3.3 and beta is 4. Well, some of these numbers are under research still, but well, this is about these numbers that we used. Well, this way, this is a power spectrum. The power spectrum, theoretical power spectrum, is the integration of these functions along the line of sight, where V is solar wind speed that is perpendicular to the line of sight. So by using an observation, for example, this the dashed line is a model, the non-dashed line is an observation. This way we can fit the model and we can find velocity in the speed in the case we know the other parameters. Also, the power spectrum of scintillation, this is the observed power spectrum, provides us density along the line of sight. Density is proportional, density is proportional to this number. G is a kind of index. This index is the measurement of the area under the power spectrum between the average spectral area. Since the number G less than 1 is Rowley's rarefaction, G more than 1 enhancement of density, and G equals 1 is about quiet solar wind. Well, another view to see the sky is one way to view the sky, the solar wind, is by using this kind of maps. Here we have sun. It's like if we view the sun from the Earth, like a corner, for example, and this is one source for a one year, for example, 3C48, and this quasar for about March starts here, auto ray moves to take place in the sky, and so on during about 6 months. It depends on the location of the source. For example, in another case, 3C, or another quasar 3C 147, that starts in uh, maybe about September here, so moves during 6 months and follows another track. What we are interested is that we are detecting properties along the line of sight, or in two-dimensional way we are detecting properties of solar wind densities and velocities in all these points. So if we have several sources in one day, we can detect at different places. It doesn't depend on the latitude, and we can detect the properties in the solar wind by using interplanetary scintillation. This is, for example, we also we are joining to the campaigns of the Parker Solar Probe. Parker Solar Probe, as you know, is a spacecraft that is approaching more and more to the sun for age perihelions like no any other spacecraft before. For example, for June 7 in 2020, Parker was about here in this kind of maps with the sun in the center, and all these points are sources, IPS sources that we are detecting with Mexar. So one of our works is during the Parker perihelions, uh, complement these observations of density and velocity that detect Parker with the remote sensing observations of solar wind by using these radio sources or the parent location of these sources and the solar wind properties there. So this is very useful for this kind of studies. Also, uh, we can all use another spacecrafts, for example, solar orbiter or even the Stellius. Oops. I'm gonna try to come back to the here. Well, one effort in the world, I said in the beginning, is the worldwide interplanetary scintillation IPS stations to help to provide information about solar wind. So one of the things we do is a format, an ASCII files that are produced daily, where we can find properties of solar wind in different places where are located or where are located the sources, or apparently are located the sources in the solar wind. This way, we would like to help to provide solar wind and real-time solar wind measurements, and also find if we can track the coronal mass ejections in the path between sun and the earth. These are the worldwide IPS stations that I said before. Here at Mexar in red, because they use all-time observation for IPS, like two big scanning array, the UTI radio telescope in India. The STEL is now named ICE, the Institute for Space and here Environment Research. This is not working more. I have to update this slide. And the MOWA in Australia, they do just partially, they do IPS mode of the arrays, ASCAT and LOFAR do the same way. What they do is provide these WIPS formats. So in the UCSD in California, in the University of California, San Diego, they developed a code that takes these results in the solar wind and uses a tomography program to reproduce all the dynamics in the inner solar wind. Like this, I'm gonna show images. Oh, okay. Here, what you observe in the left, we have the sun in the center in red and in blue here. This image it was made by using observations with the UT radio telescope. Was made with thousands of observations to reproduce the density distribution in three-dimensional way using this tomography model, the program of the UCSD. On the right, you can see distribution of speeds in the solar wind. In this case, it's a two-dimensional tomography where the sun is at the center. Also, the sources that were detected, the IPS sources detected are shown in little circles, as you can see. In this case, we used observations of Japan, the STEL, and also in observations with MEXAR. So the idea is to get observation of all these observatories to reproduce in a better way this kind of maps, and also this kind of maps in quasi real time. Okay, so another fields of research that we can explore with MEXAR, not just IPS, that we mostly do. One is now that we improve the observations with the digitalization of MEXAR, we can explore in a better way solar radio bursts, ionospheric scintillation too, pulsars. You have any doubt about this? I can explain later during the questions. Also, map of the sky, as I showed one image, fast radio bursts that are that is a new field of research in the recent years. Catalog of MEXAR at 140 megahertz, and also this is something that is most and most we are having more and more problems, and all the work with radio telescope has more challenge with filtering and mitigation of RFIs, radio interferences. Okay, I want to show some examples. This is ionospheric scintillation radio sources. Sometimes scintillation is normally this during the evening, for example, when you observe the horizon radio sources, when the line of sight crosses by the atmosphere, you observe scintillation go to ionosphere. However, sometimes during strong geomagnetic storms, we can also detect this kind of behavior, that is the flux fluctuations during geomagnetic storms. This is an example of this source, Cygnus A, at this date. So we have several observations where we find this kind of storms, and also is observed this kind of behavior. So it will be interesting to study how we can monitor the ionosphere by using ionospheric scintillation with using Mexar. Also during active reading, we all days observe the sun during about 10 minutes, and we have, I don't know, sometimes solar spots, sunspots, and the active region produces that the flux increases about 10 times in radio. Not also the flux, also the noise has a, can characterize this noise to identify what kind of active region we are observing. For example, not all the active regions produce or these very intense fluctuations. It depends also on in the configuration of the magnetic field of the active region. So this is one thing that we would like to explore. Even also we have observed this kind of flares. So, there are more often flares during this increase of the maximum. We have several records of this kind. You have here an image of the plot of GOES showing an M9 flare here at the maximum. So in this case, for example, we observe, these are sequence of images for each part of the increase. This is the active region that produces the flare. And we observe it with Mexar here about 4 minutes. So this observation is influenced by the flare. So we have another kind of noise, another kind of signal, an increase of the flux that is produced by flares observed at 140 megahertz, and it's something that we would like also to explore. But some final comments. And I say Mexar reaches all its potential to reach the expected sensitivity that we didn't have in the past before the year 2020. Now we have increased the number of sources that we can detect, and we can also now increase the resolution to figure out the solar wind by IPS. Also, we had the opportunity to address different areas of research: ionospheric scintillation, pulsars, radio sky, solar and fast radio bursts, and a new catalog for Mexar. However, there are also challenges. What we have to deal now, the increase in the amount of data require higher efforts to implement software. Something that I would like to do also is report daily real-time solar wind conditions by IPS observation. This is something that we are working now. For space weather purposes. Other is that the noise in the observations has increased. Now we need algorithms to identify and mitigate this noise, and I say. One thing that is also interesting is to find the right bandwidth for different studies. We still don't know if we have to apply all the bandwidth, for example, for IPS, for observations of IPS, or for observations of the sun, or any other kinds of studies, because we have to understand very well what's the response in all these bandwidth, because the data are very big. So maybe we can use just some fraction of this big bandwidth to explore certain studies. Well, here I left you with an image of Mexars in the back, and this is the Laboratorio Nacional de Clima Espacial. As you know, the collage is gonna be in Mexico, Monterrey, Nuevo León. We are not near Monterrey, but you are invited. If you are in Monterrey, maybe you can have a trip here to Mexico. It's about some 600 kilometers. You have to take a plane. But in any case, you are invited to come. If you want, you just write me, and I will be sure that you have a tour in this Laboratorio Nacional de Clima Espacial. So this is my contact. So I want to wait for your comments or questions. Gracias.
Okay, Dr. Julio, thank you very much for your talk. I'm going to check our chat in YouTube. Okay, we don't have questions, but I have some questions. The first one is, how do you distinguish between fluctuations due to interplanetary scintillations and scintillations due to the ionosphere?
Good question. Well, basically, ionosphere scintillation is typically about the 0.1 hertz in frequency, and IPS typically 1 hertz frequency. Yes, that's the principal way to distinguish. This one has a cadence more slow, the ionospheric scintillation.
Okay. There are some events that could generate some fluctuation similar to the interplanetary scintillation.
Yes, we can even confuse sometimes noise. We have to be very careful to validate the observations, because you know that the time series that you get from the observation that is polluted with noise. So there are ways to identify in the spectra when you have at high frequencies a big power than the power that in the region of IPS. You can assume that you are inserting noise or confusing noise with IPS. So the best way is to try to clean the data, or in the worst way, to drop the data.
Okay. The last one is there some privileged site to install this type of telescopes? Or the idea is to have them all over the world?
Well, yes, the idea is to have the most telescopes in different longitudes. For example, when in Japan, you have to observe during the daytime, because you only can associate solar wind properties to observations that are in an elongation less than 90 degrees. So this is the same as we observe in the day side. So for example, in Japan, they are observing during the day side, but during the night they lose all the observation in the solar wind, and they come back at the next day. But we could provide the daytime observation of the solar wind properties during the night side in Japan, and they can provide us by the other way during our night side the observations of solar wind we require. I'm not sure if that's response to your question.
Okay. Okay, we don't have more questions, so thank you again, Julio, for your talk, for your time. And well, we hope to see you soon in our next talk. Bye.
Gracias.